Now, you've probably been asking your computer screen over the past couple of days, well, what about voltage under non-standard conditions? So what happens if you're not at 1 molar or 1 atmosphere or 25 degrees Celsius? And you're absolutely right, that is a big concern, because here's what happens with a voltaic cell. So here's our popular zinc-copper voltaic cell again. So we've got our salt bridge, we have our zinc and copper electrodes, we have our zinc ion solution, and our copper ion solution. So the instant this reaction starts, in the room we'll say it's 25 degrees Celsius, and that the concentration of both of these solutions, so the zinc ions and the copper ions, are both 1 molar. And during the course of this reaction, then, electrons are going to be transferred from the zinc over to the copper. And that's going to generate more zinc ions as the zinc breaks apart and turns into zinc 2+. And so the concentration as a result is going to increase over on this side. You're going to increase the concentration of Zn2+ because you're generating more Zn2+. And over on this side, as those electrons come over, they're going to join up with the Cu2+. And so the Cu2+ that were in there at one time are all going to get used up as they absorb electrons and turns into solid. So the concentration on this side is going to go down. And so the concentration of our reactants here at the cathode are going to decrease, and the concentration of our products here at the anode are going to increase. As this happens, the electromotive force, the voltage, is going to slowly decrease. And so really what we've been calculating as the E standard of the cell, hey, that's just a fleeting thing. The second that reaction starts, you're going to increase the concentration here, decrease it here, and that E of the cell is no longer going to be true. But it's still a good thing to calculate so that we kind of get an idea of how the reaction pairs up with everything else and what it's going to be. For the most part, it won't vary that much from what it started out at. However, over time, eventually the concentrations are going to get to the point where the electromotive force will decrease to 0 volts. If this was a voltaic cell or a battery, we would call the battery dead. And we can explain the dying of these batteries by Chatellier's principle. So Chatellier's principle says that when you stress a system, it moves in order to relieve that stress. So if we consider a voltaic cell composed of a copper electrode and silver ions turning into copper 2+ and silver, if we were to, let's say we increase the concentration of silver above the 1 molar, so above what it is at standard state, that means we've got a large amount on this side which is going to drive the reaction over towards the other side in order to alleviate that. As a result of the reaction being driven over towards this side, we're going to increase the rate of the forward reaction, so this reaction will occur faster. If it occurs faster, the voltage will increase, and the electron flow, or the current, will also increase, just by increasing the concentration of this guy. So even though this is an equilibrium problem, the same basic principle, the Chatellier's, applies to this. By increasing the concentration, we increase the rate of the reaction, and therefore we increase the voltage. However, in an actual voltaic cell, where this is going to be getting used up as the electrons are transferred over from that one, we're going to wind up slowly decreasing the concentration of Ag. And as that concentration of silver ions decreases, the rate of the forward reaction is also going to decrease, and if it decreases, the voltage decreases, which means the current decreases. And eventually this concentration will get so low that the voltage will reach 0. And if we come over to the product side and instead look at the copper ions, if the copper ions are greater than 1, so if we increase the concentration of that guy right there, the rate of the forward reaction is going to decrease. And that's because we've put stress on the product side, and so it's going to be pushing back towards our reactant side. And so that means our voltage is going to decrease, and the electron flow is also going to decrease. But if we were able to remove the Cu2+ ions as they were formed, and so that's going to decrease the concentration of the 1 molar, then it's going to be able to plow forward with the reaction. So the rate of the forward reaction is going to increase, the voltage will increase, and the electron flow will also increase. And so in both cases, this value right here, this standard of the cell at 0.46, is going to be a very, very short-lived number at exactly that value, because as the concentration of this decreases, the concentration of that increases, it's going to cause this value to drop over time. So here's a question then. Let's say we have a cell that was at standard state conditions and it was functioning according to the equation that's written right here. It'll run until zinc 2 plus is equal to 1.14 molar. And we want to find the concentration at that point of the gold ions. So notice that this reaction is at standard conditions, which means both of our ions in the solution are starting out at 1 molar. Okay, so right at the beginning they are at 1 molar. But as time goes on, it's gotten to the point now where the zinc ions have increased. So that's our products increasing like they're supposed to 1.14. So it's gone from 1 molar to 1.14 molar. So at this point in time, when the concentration of zinc is now 1.14 molar, the question wants to know, what's the concentration of gold? So if we started with 1 molar of zinc 2 plus and now we're at 1.14, that means we've generated 0.14 molar more of Zn2 plus. And where did that 0.14 come from? Well, it came from the zinc solid that reacted with the gold. So that means it's all just a reaction stoichiometry problem. So if we started with 1 molar, now we have 1.14. That means we've generated 0.14 moles of Zn2 plus for every 1 liter of solution. And then from there we can just do a simple stoichiometric conversion. For every 3 moles of zinc, there's 2 moles of gold that were used. And so it's going to be, so 2 moles of gold were used for every 3 moles of zinc that were generated. And so then that makes moles cancel out moles of zinc. And so now we would just solve this out. We're going to find the concentration to be 0.907 molar. And that makes sense. So the concentration of the gold decreased and the concentration of the zinc increased, which means that the voltage of this cell is going to decrease as well. So this brings us to something cool called the concentration cell. So you can actually make a voltaic cell run even though you have the same species at the anode and the cathode. So instead of having like copper and zinc, you could do one with copper and copper, or with zinc and zinc. So according to the E of the cell calculation, it should equal out to 0 volts because you would have the same thing losing and gaining, so it would wind up being 0. But that's standard state conditions. If you have non-standard conditions, so concentrations that aren't 1 mole on either side, you can cause it to drive from the anode to the cathode. So you do this by taking the concentration of the anode and making it less than the concentration of the cathode. And then it will cause the reaction to proceed so that the anode will increase and the concentration of the cathode will decrease, just like it would in a regular voltaic cell. And when the concentration of the anode equals the concentration of the cathode, then you're going to wind up with your voltage of 0 again. So here's an example. We have 2 nickel plates inside solutions of nickel 2 plus, and on this side, on our anode side, we have a very, very diluted solution, so not much Ni2 plus on this side. Over here we have a very, very concentrated solution of nickel 2 plus, so a large number of nickel 2 pluses. That's going to help draw the electrons from this side over to this side. As the electrons are coming over, this nickel 2 plus that's concentrated is going to form into nickel solid. The nickel solid over here is going to dissolve into nickel 2 plus and go aqueous. And so eventually as time goes on, the concentration over here will go down, over here it'll go up, and then those concentrations will be equal. This light bulb will turn off.